right, we are now at a new experimental design. We have three experimental groups and one DV. Specifically, this design is between subjects, so each participant is only in one of the three groups. This is very similar to between subjects t-test, except now we have an additional mean. So we have three means we're comparing. So you want to, with an ANOVA, you want to know if there is some difference among your three means. Your null is there is no difference among your three population means. Another way to see that is your population F statistic is 1. Um, your effect size is called eta squared, where small is 0.01, medium is 0.06, large is 0.14. This is percent relationship between your IV and DV, so it's very similar to R squared. Eta squared, R squared. Any squared statistic is going to tell you percentage in proportion. So what I mean by percentage in proportion is 0.01 times 100 is 1%. What does the F statistic tell you? Well, it actually tells you your ratio of independent variable variance to error variance. This is signal variance or noise variance. I did talk about this in class. I'm not going to teach it again. What your data will look like. Participant A was in the anger condition. Their political aggression was 5. Participant G was in the neutral condition. Their political aggression was 3. There are 3 conditions of your independent variable, and you are measuring political aggression as your dependent variable. So you will see that in Jamovi right here. There is not much that I can do here with the... You can change order around and things like that, but ultimately this is a nominal variable. This participant is an ID variable, and political aggression is a continuous DV. Now, there are lots of ways to run the ANOVA. You can run a one-way ANOVA, or you can run ANOVA. I'm going to run the ANOVA command just simply because I like it better. So I click the ANOVA command. My IV goes into fixed factors. My DV goes into dependent variable. My effect size is eta squared. That is essentially what I want. Now you have all these other options you can do. I'm going to show you, we're going to have to run another test to get the non-parametric. So we're going to do that in a second. So there's a lot of steps involved with ANOVA. Ultimately, I want to get post hoc tests for each variable in my condition. I want those 95% confidence intervals. Ultimately, at the end of the day, you have correction options. You have no correction if you predicted your mean differences, predicted the follow-up test you were going to look at, you use no correction. Tukey is the most common form of corrected p-value. And Bonferroni multiplies your p-value by the number of t-tests you ran. That's the one we talked about in class. I'm going to leave all 3 of these clicked. If it were my data, I'm predicting mean differences and using no correction and pre-registering my hypothesis. If it's your data, I'm using Tukey or Holm. Okay? I would never use Bonferroni in actual data. It'll just tell you everything's non-significant, but that's fine. Then finally, just to sort of I like the estimated marginal mean plots. And I clicked the observed scores just to see what it did. It gave me those dots. I like those dots. We're not going to worry too much about these options. They're kind of advanced, but that's what I click. The things and I'm not going to get everything from this, and we'll see that in a second. And we're going to have additional steps to get everything we want from this. But let's sort of see what we got here. This is our first run. We ran the ANOVA, right? What do we have here? So we have our F statistic. Our independent variable caused 25% times more variance than our estimate of error. That is significant, and our eta squared is 0.894. Our IV caused 89.4% of the changes in our DV. That's what's happening here. So that is a significant result. When you have a significant result, you go through and you do your post hoc tests. But before we go there, I want to look at our means, right? So in terms of what I would have predicted, I would have predicted that the anger condition has the most aggression, the neutral condition has the second most, and the happiness has the third. And so I just want to go back in. What I'm seeing here is that my predictions were correct, but I have one of my Cohen's D's that's off. So I'm going to go back into my data, going back into my anger condition variable, and I'm going to put them in order that I predict again, just to see if it does what I think it's going to do. I've never done this before. I've just checked it out. And it did. So as you can see, all my predictions kind of were true, right? And I'm not going to talk about everything here, but my Cohen's D's are all positive now. So if you align your levels to be in line with the one you expect to have the most political aggression, the middlemost, and the lowest, so highest, medium, low, if you organize your levels in your variable in that condition, your post hoc tests will match such that a positive Cohen's D indicates in line with my hypothesis. In this case, we have a negative Cohen's D in the 95 CI. That means it goes against my hypothesis. So we'll just talk about this real quick. Let's do anger versus neutral. It is significant. It is not significant with Tukey. It is not significant with Bonferroni. If I predicted it, I get to write it up as significant. If I didn't, I don't, right? We talked about that. My 95% confidence interval of Cohen's D is potentially a negative small effect in the opposite direction from what I predicted to a large positive effect in the direction I predicted. So I predicted that people in the anger condition would be more aggressive than those in the neutral condition. Well, I don't know. It could go the other way. It could be a small effect in the other way or a massively large direction in the direction I predicted. Okay. If we do anger versus happiness, we get our p-value that's significant. It's significant here. It's significant here, right? You can see that the Bonferroni is always the highest p-value. It's the most conservative test. If it were my data and I predicted it, I'm using this p-value. If I didn't predict it, I'm using Tukey's, okay? This is just to show you the Bonferroni correction because you are taught that. This is a large effect, and it could be between a large and large effect in the population. I know this is a large effect. I'm done with that one. Neutral versus happy, we are getting significance, significance, and significance. The effect size is large. It's between a small and large effect. So it's a discovery as well. You do follow-up tests when you have significance. I like these tests here because they show you the 95% confidence interval of Cohen's D, which is awesome. That's great. The one thing, we have our pictures here. We have everything we need, right? So that's what it means. Remember, sum squares divided by degrees of freedom equals mean squared, which is variance. Sum squares divided by degrees of freedom equals mean squared, which is variance. Variance of my condition divided by variance of my error equals my F statistics. So 8 divided by 8.444 divided by 0.333 equals 25.333. I just wanted you to show that. But that's the last thing I'm going to say with this first analysis. That's one of 3 things that we have to do. Our next analysis that we have to do, we go into our ANOVA. Our non-parametric one-way ANOVA is our Kruswalski-Wallace test. And since we have the ability to do this, we're going to do this. You know, we don't need to worry about the effect size or anything like that. This is our non-parametric test. If this is non-significant, it will suggest that our other result that we just reported on, this p-value, was due to a violation of assumptions. It is significant. This is not due to a violation of assumptions. There's one more thing we have to do. We do not have the 95% confidence interval of eta squared. We need to get that. Unfortunately, we have to use an outside computer to get this. That will be in the next video.